so weird to hear. Used to not having any audio in here, and it's probably better that way. That way, if anything happens on Zoom, it doesn't distract from the class. Usually people are pretty good about that. Anyway, upcoming announcements. Let's see, we had an assignment due yesterday. A new assignment was revealed due next Wednesday. As always, you can submit that early and the grader will attempt to turn that around faster than ahead of the exam. I'll reveal the study guide for exactly how much material is on the upcoming exam tomorrow. But we're basically through that content. There's no second pumping lemma on the second exam. So that's the next thing we're going to cover after we finish off the next 6 or 7 slides talking about NPDA conversion and DPDAs. Then, so yeah, study guide tomorrow, exam next Friday. Just about everything. I guess there's the project as well. And the project was due the week after the exam. So you have 2 weeks and a day left on the CYK project. So now that you've had a chance to get some practice with that on homework, it's time to start thinking about designing a program that does that for an arbitrary grammar. So I mentioned this yesterday, but if you'd like some hints getting started with that or to talk about designing out a solution, these are the great office hours for that because there isn't an assignment due in the next couple of days. So I'm not going to be quite as busy with assignment questions. So very good time for that. I have the time in my schedule to help you get started. So that's everything going on. Any questions before we dive back into context-free grammar to non-deterministic push-down automata conversion? See, I don't think anyone in here was in my office for the joke. I was going to start today's lecture in German just because we were talking about different languages in class and converting things to different languages. But it'd been really funny to just start talking in German. Like, oh, wait, that was a joke from yesterday. Okay, so we stopped before we were able to go over a solution for this, right? I think we were going to go over a solution to this first thing today.
Yeah.
Wow, my memory did something right for once. We should just stop class and just throw a party. All right, so I'm going to start making the assumption that in our initial state for NPDAs, that we have the bottom of stack symbol on the stack already. So moving forward from that, we need to look for this conversion, push the start non-terminal onto a stack. So to do that, we're going to make no read from the input. We're going to pop the start non-terminal and push the start. Sorry, we're going to pop the bottom of stack character, push on the start non-terminal on top of that bottom of stack character. Going to a very large Q1 that is going to have all of the associated transitions. We need to make one of these transitions for each one of these productions. And the general form of that was we're going to read from the input the terminal symbol because this is in Greibach normal form. We're going to pop the non-terminal that is the left-hand side and push all non-terminals that are the right-hand sides after that terminal on the right-hand side of a production. So we need now 6 transitions to represent all 6 productions of this grammar. So the first one is going to read an A. We'll start down here. Pop the left-hand side, which is an S, and push the right-hand side non-terminals, which is an A. Next one, let's do all of the A's up here to keep them together. Keep 3 and 3. We can read an A, pop a capital A, and push a capital A, B, C. We could read a B, pop the A, push the capital B. We could read an A, pop a capital A, and push nothing. Note that this is where that non-determinism is apparent now, where we have 2 reads of the same input character, the same top of stack symbol, and we have 2 different things that we could push. That is true non-determinism in NPDA form. We will see when we start talking about deterministic push-down automata that we can read the same input character as long as we have differences in that stack symbol. or read the same stack symbol on the top as long as we're reading different input symbols. In order for it to be deterministic, we're looking at differences in the tuple of those pairs. We'll get to that in a second, but the non-determinism is baked in when we have the same tuple as the first two elements here. We read the same character and look for the same top of stack character. If that pair is the same, then we have non-determinism. Last two transitions, the B and the C. So we could read nothing. No, it's reading a B. My brain is working. Read a B, pop a capital B, push nothing. Read a C, pop a capital C, push nothing. So that's everything from Q1 to Q1. Then we reach a final state. We have to look for the bottom of stack symbol again. So we read nothing from the input, pop that bottom of stack symbol and push it back on to get to a final state that is Q2. And then we accept if we are in the final state with an empty stack, allowing for that bottom of stack character to be on the stack and or at the end of the input. All three of those things are true, then we can accept. So here is an NPDA that represents this context-free grammar that has already been converted into GNF for us. If it weren't in GNF, we would have had to convert it into GNF before going through this process, just to make it easier. It's not to say it's impossible to have done otherwise, but the algorithm for reading the grammar and converting it into an NPDA, very easy if the grammar is in GNF. Questions on this process? Is this what people had from yesterday / preparing for today? All right. Any questions? Everyone have what they need? Okay. As always, on the slides, I'm writing up the transitions because the actual state machine form looks kind of gross. So oftentimes I find it easier to break it down into very assembly-like instructions. Here's the initial state transition rule. Here are the middle transition rules. And you could break those down into those that are based on the S production, the A production, the B production, if you wanted further titles for those. And then we have the acceptance of the final state, and that is the entire NPDA written in transition form. We could go the other direction. Given an NPDA, construct a context-free grammar that represents the same language. So when we have this, the stack characters are the unexpanded non-terminals. So whatever the stack symbols happen to be, that's what you're going to use as your non-terminals as you build the grammar. At the end of that, you could go through a translation process and convert the non-terminal symbols, whatever the stack alphabet was, into something that makes more sense as non-terminals in a grammar. So if the stack alphabet were binary, it doesn't really make sense to have binary as your non-terminals in a grammar. But as you're building this up, don't go through the translation process every single time you're reading. Use that as the non-terminal as you construct the grammar, and then go through and change the zeros and ones. We're going to make a couple assumptions about the NPDA's form. Rather than having multiple final states, we're going to assume that there's a single final state that can only be entered if the stack is empty. And you can always create this out of any other NPDA if you wanted to. We won't go over that process, but there is a process to do that. And then the other is to only increase or decrease the stack count by 1. If you're increasing the stack count by more than 1, then you can create an equivalent NPDA that just has more transitions in it and more intermediate states. So again, there is a translation process that gets any NPDA into this form. Since we only allow for a single pop, the most the stack size is decreasing is by 1. So we can reconstruct an NPDA if both of these assumptions are met. We're not going to go through it. because it's pretty similar to the exact opposite form that we would have gone through. But it is important to know that we can reverse this process as well. This is kind of the intuition for how you would do that. The important thing we're going to cover, though, is determinism. And I hinted to this entire process, but let's go through it in more detail. Restrictions placed on an NPDA to turn it into a deterministic pushdown automata. There has to not be non-determinism, and the only way to have non-determinism is if we have that same tuple of input symbol red and top of stack symbol red. So to be deterministic, if we have that pair, input symbol stack top, then at most one move can be made from each state. So this means that a DPDA can have lambda transitions, which is interesting. That's not something that we're familiar with from DFAs and NFAs, but we allow lambda transitions. Why is that? Because we need the tuple to be the same. So if one or the other of those is a lambda, then that's okay, as long as there isn't any other conflicting. Like if we were reading nothing from the input, then we can't, on the same top of stack character, do something. This would say when we see a capital A on top of the stack, then we could either do nothing or make a move. And we can't have that level of ambiguity. That is non-determinism. So just like with the DFA, at all times, at any position, there is only one move possible. But that is possible with lambda transitions in DPDAs. One thing that is interesting to note about this process is that, remember back to regular languages, we could freely convert between DFAs and NFAs. However, there is no such conversion in context-free languages, and the reason for that is that they don't represent the same language class. DFAs and NFAs both represented regular languages, but NPDAs and DPDAs don't represent the same language class. So context-free languages, the same language class that we had for context-free grammars, maps to non-deterministic pushdown automata. DPDAs are a separate language class that is smaller. So only some NPDAs have equivalent DPDAs. But every DPDA, of course, has many possible NPDAs. So it's a smaller language class. Deterministic context-free is the name of that language class. Let's give you an example. Here we have two languages, A to the n, B to the n, and another language, A to the n, B to the 2n. So first, why is L1 context-free? We've seen this before. We could write a context-free grammar or a non-deterministic PDA for it. The English behind this, when we see an A, we're going to push something onto the stack. When we see a B, we're going to pop it. How about language 2? Why is language 2 context-free? Now think about this in terms of an NPDA. How would you construct an NPDA for A to the n, B to the 2n?
You can maybe push two A's.
Yeah, we're trying to map a future A to two future Bs. So if we put two A's when we see an A, then we're saying each one of those represents one of the future Bs that we're going to see. So we could easily do that. But now, what happens when we define a language that is L1 union L2? we're going to OR these together and accept both a to the n, b to the n, and a to the n, b to the 2n. How would you build an NPDA for this? You could do it, you just non-deterministically either add 1 or add 2. And you go down a path where when you branch from that initial state, every a that you see either it does the same thing that the first one did. It either adds 1 or it adds 2. And since you can fork that process into 2 children, if one of those children returns true, the string matched that form, then you accept. But non-determinism is built into that NPDA. There's no way to build that without the non-determinism. So because of that, this language is non-deterministic. And so it is context-free, but not deterministic context-free, because there is no such deterministic solution to the problem. So this language is context-free. And the way to imagine that it's context-free, you can go back to the grammar idea of we can write a grammar for the left-hand side, a grammar for the right-hand side, and just introduce a new rule. S arrow L or R that produces the left-hand side or the right-hand side, where L and R are the original start non-terminals for the left-hand side and the right-hand side. And there is our complete grammar. We have the left-hand side starting with S1 here, the right-hand side starting with S2 here. Then for S1, that maps to A to the N, B to the N. The form is AS1B, and that forces there to be the same number of A's as B's. For the right-hand side, we have AS2BB, forcing there to be 2 B's for every A. And we just decide immediately which is the form, A to the N, B to the N, or A to the N, B to the 2N. But when we're parsing this string from left to right, and we see that first A, we have to make the decision on that first character, whether the entire string adheres to the left-hand side or the right-hand side. And since we can't go back, we can count the A's and know how many there were, but we already on our stack needed to have enough symbols to map there to be the exact number of B's or twice as many B's. You can't non-deterministically do both of those at the same time. You would need 2 stacks to be able to do that. And we only have 1 stack. So the grammar has to immediately decide which form the derivation will be, left-hand side or right-hand side. That is the non-determinism baked into the language itself. There is no deterministic solution to this. So this logic is possible with an NPDA. We just branch immediately, non-deterministically on the start state. With a DPDA, you can't have that non-determinism. We can't look at an A and both push 1 A and push 2 A's at the same time. Fork a child, 1 does each. With a DPDA, you're looking at the same input symbol, an A, and top of stack character, the bottom of stack characters. So you would want to do 2 different things in that same tuple of input character, top of stack character. So do note, this is not a math proof. A math professor would say, you can't go on here, you need to derive the proof. And I would say it's intuitive enough at this point for computer scientists. This is why I'm not a math professor. Don't let them know. They will attempt to get me fired. So reasons to study DPDAs, deterministic context-free languages, is by definition, they can be efficiently parsed. There exists an efficient parse for every deterministic context-free language. So if you have a context-free grammar and you ask the question, can I make this non-deterministic grammar deterministic? If you can make it deterministic, then you know an efficient parse exists. You can do better than just CYK. In fact, you can do something LL or LR, which is, we'll go over that at the end of the quarter, but that is wonderful. And only some non-deterministic grammars can be parsed efficiently. So because there's only one possible move at each state, rather than an arbitrary number, the number of processes we need to fork at that point, then we know we can terminate in a number of moves proportional to the size of the input. As an example to this, we have in the input string, we've matched part of the input to the form that is the non-terminals. So we've expanded to this point. And there's a part of the input that we haven't read and a part of the string that is still represented as non-terminals. And we can, on one pass from left to right in linear time, be matching that and creating, since there's only one move to be made at each point in time, you can convert it into the equivalent of GNF and straight parse with no non-determinism. Very nice. So we introduced the concept of a simple grammar, and it turns out that a simple grammar matches to deterministic pushdown atomic. It's that same language class. So simple grammars represent deterministic context-free languages, and if a simple grammar exists for a language, then a DPDA also exists, which is really cool to see. So it's a relevant language class, yeah.
Does that go both ways? So if the DPDA exists, a simple grammar?
Yep. Very nice. When we have a simple grammar, there's only one choice of production to apply. We don't have that same tuple of non-terminal character, first character of input that comes from that. So it's exactly the same idea. So the rules of the simple grammar match with the rule preventing non-determinism in an NPDA or DPDA. Apparently, I did not animate the next slide correctly. I think I say that every quarter. I think it's actually the rest of the slide deck. Oops. So simple grammars, which are nice, can't represent all aspects of programming language syntax. The reason we adhere and look at context-free grammars and context-free languages for parsing is it is able to handle every aspect of programming language syntax. But there are parts of syntax that can be broken down into deterministic forms, which is nice. So we need the ability to parse less restrictive grammar types. And we'll talk about LL and LR grammars later on, but here's kind of a brief introduction to them because this is where they would naturally show up in the curriculum. But I don't want to spend time talking about them now because I want to also have talked about compilers and a bit of computation theory before we dive into it so that we can see how LL grammars tie into everything that we've talked about. It makes much more sense as the last thing that we talk about. But the basic idea of an LL grammar is how many characters of a look ahead do we need in order to be able to deterministically make a decision about what production to apply. So an LL1 grammar is deterministic because with a single character look ahead, we can tell which character, which path to take in a grammar. But an LL2 grammar requires a 2-character look ahead to make that deterministic choice. An LL3 grammar would require a 3-character look ahead in the string. And whenever you're looking more than 1 character ahead in the string, there is a computation cost associated with that scales with that length. But it's something that is not too bad and can stay linear with an intelligent application. So giving an example of this grammar, S arrow ASB or AB, it's an L2 grammar because if it were LL1, then we'd have to be able to look at this A and make a decision. When we see all we have in the string is an A. We see that there is an A in the string. Should we take the left-hand side or the right-hand side? We don't know, it's ambiguous. But as soon as I add a second character to this, one option is an AA, one option is an AB. As soon as we see AB, it has to be the right-hand side because the second character of AB is a B. But if we do ASB and expand, there are 2 options. Can expand to either AABB and have the S go away, or it can go to AASBB. But regardless, the first 2 characters are both A's. And this would tell us that if we see AA as the first 2 characters in this string, we want to pick the left-hand side because there's no possible way the right-hand side could derive that. So if there is a way for the rest of this string, AA something, to be matched with this grammar, it would have to be down the left-hand path. So it's LL2 because it requires a 2-character look ahead. We don't need more than 2 characters to determine left or right, but we need at least 2. Questions on that idea? We'll come back to it in a lot more detail later on in the course. And as a hint, an LL1 parser is your second programming project. So a little bit more about them. Is the grammar up there an LL grammar? If we have a single character, we scan the first symbol, which one do we choose? It's ambiguous. First 2 symbols, AA, still ambiguous. It's not LL2 because we need more than 2 characters to determine it. And it turns out that no matter how far ahead we look, there is no distinction between the SS and the ASV with regards to the number of A's that could be at the beginning of the string. So this is where non-determinism is baked into the grammar, that no remote look ahead of any size is going to be able to determine whether we need to look at the left-hand path or the middle path. So we need to fully explore that non-deterministically and halt if there is a problem. Sorry, halt if we end up with a solution. And that process is a lot more complicated. So if a grammar is not an LL grammar, we could either attempt to convert it into an LL grammar. There are equivalent forms that are LL or not LL. And you can increase or decrease the length of the LL1 versus LL3 versus LL12 by converting to equivalent grammar forms. But it may be completely baked into the language itself that there is no equivalent form that is LL or is less than LL of some constant K. And so a lot of our existing programming languages can be defined by LL grammars. A lot of the existing compilers that are out there are written using LL parsers because they're very efficient. But not a complete and total mapping between deterministic context-free languages and LL grammars. So because of this, there are LR grammars, and some deterministic context-free languages require LR grammars, which are even more complicated than LL. And we'll go over that as the very last thing we do.
What does LL stand for?
It's left to right, leftmost derivation. And then LR is left to right, rightmost derivation.
Not LLL then.
Because it's all hyphenated. And something that's hyphenated doesn't have an extra letter associated with it. Left to right is left dash to dash right. So it's the only capital letter in that. If you want to, though, you're absolutely welcome to write L T R L. It's like control, but with an L at the front. Literally. So yeah, we're going to come back to this after we fully look at compilers so we can look at LL grammars and get a little bit more out of them than just the abstract idea. We want to see them applied to that concept, which is why we're going to do everything else in the class and then come back to this. So very brief introduction, very much sprinkled. I don't expect you to remember most of this by the time we come back to it, but it's just an introduction to the idea. How are we doing? You said good, it's because you didn't know what's coming next.
Oh, God.
Pumping lemmas part 2.
It'd be really funny if you added that slide and like a sound effect. Like, that's really
Yeah, the last slide deck ends with kind of this level of optimism, like this seems like a cool problem to go explore.
Yeah.
And then I immediately transition into one of the least favorite things that we've studied so far. Let's do that again. I like to create expectation and subvert it. It's a good thing we're using the black marker. I said it's the color of my soul. So I'm really making that happen. All right. Luckily, I get some mixed feedback on this, but most people tend to agree that if you have a solid understanding of the regular pumping lemma, that the context-free pumping lemma makes a lot more sense. So even though it is more complicated than the regular pumping lemma, it's not more complicated to learn than the regular pumping lemma was to learn, given that you understand the regular pumping. So if you are a little rusty on the regular pumping lemma after your homework, in addition to having a great preparation for the upcoming exam, for which there will be a regular pumping lemma problem on that exam, there is a great chance, or a great reason to review it ahead of talking about this. So it's worth going back and reminding ourselves the pumping lemma for regular languages, because the purpose of the pumping lemma for regular languages was to prove that a language wasn't regular. We have now, again, shown ways to show that a language is context-free, so we need to be able to prove that a language is not context-free. Pumping lemma said that all regular languages have a particular repetitive pattern, assuming that there are some number of states in an accepting DFA. As soon as we have a string that is longer than that, then we have to have some cycle in that DFA. We can identify where such a cycle is. It's within the first number of states characters of that string. That creates a cycle, but we can repeat some number of times. If we can pump that cycle some number of times, such that we can guarantee, we can prove that regardless of the length of that cycle, it creates a string that is not in the language, then we can prove that the language is not regular, because any existing DFA would have to be able to produce a string that is not in the language. Therefore, that DFA can't exist. So we talked about this in terms of the finiteness of the number of states of a DFA, and that helps a lot. It was very visual, which was very nice. Unfortunately, for context-free languages, we don't look at the NPDAs to construct this. We're going to look at context-free grammars. And we're going to look at, instead of cycles or loops in a state machine, we're going to look at recursion in a grammar. All right. Questions on that before I move on? I just want to, it's a pumping lemma. We got to stop at every possible point to make sure everyone's with us. Otherwise, it creates lots of future headache. Any questions on motivation, remembering the regular pumping lemma, why it works at an intuitive level? The intuition there will really help with the intuition for the context-free pumping lemma. All right. Thinking about a grammar, if we're going to create an infinite number of strings, there has to be recursion in the grammar. We can't just have a kind of like a DFA. We have to be able to create a cycle. If we had a DFA with some arrows to other states that had arrows to other states, if we didn't create a cycle at some point, the language is finite. There are only some number, if some of these states were final, there are only a finite number of strings in the language. In order to create an interesting language, there has to be some cycle, because then you can iterate that cycle to create any number of strings that are in the language. As long as on some path from an initial state to some final state, there is some cycle. Suddenly the language goes from finite to infinite. There's no larger finite. It just goes to however many strings there were, now it's infinite. Similarly, in a grammar, you can have something like S arrow, some stuff with some A arrow, some stuff with a B arrow, some stuff with a C, etc. As long as you're doing this, you can create a finite language. But as soon as you allow for some kind of recursion in this, so maybe this B goes back to an A, and then has some ability to terminate at some point to create an actual string in the language. It's not just an infinite recursion that doesn't add anything. We saw that when we talked about our useless productions. As long as this isn't a useless production, then we can now recurse A to B to A to B to A to B and end after any number of those recursion. So it's like a loop. This is why recursion and loops are the same idea in programming languages. It's exactly the same idea. So there just needs to be some recursion somewhere in the grammar. This could be B to A, this could be B to S. It doesn't have to be just a back and forth. This could create an S to A to B, B to S, S to A to B, B to S. There's some recursion that we can terminate after 0 repetitions of that, 1 repetition of that, 2 repetitions of that, etc. Question?
So that still work if it was like, S goes to A, like with a little a.
Something like this?
Yeah, where you're adding characters, does that still count?
Yes. Yeah, so if we do this 0 times, then we haven't added this A at all. If we do it 1 time, I guess 0 times, we still have to get to the termination point. So we can add 1 A or 2 A's or 3 A's or 4 A's through this process. Yeah, we need at least 1 terminal in here in order to grow a language of some kind. But all we're going to focus on or care about are the non-terminals for the moment, because that tells us where the recursion is. But that recursion takes a particular form, kind of like the XYZ from the regular pumping lemma. So here's an example of self-recursion. A can, through some sequence of productions, reach some string V, followed by a capital A, the recursion, followed by some string Y. And then there's a way to terminate from this, getting a string that's in the language, producing this X. I'll have a visual way of representing this in a moment, but we can recurse, and the X is guaranteed. If we have 0 repetitions of this recursion, we get the string X. That creates the termination. We could recurse this once, getting Vy, recursing in the middle, and then terminate with X, and we would end up with Vxy. We could do this twice, end up with VVXYY, etc. So a very similar idea to the loop, except now, because it's a grammar, you can have a part of that on the left-hand side and the right-hand side. So instead of pumping once in the middle, we're going to be pumping the string that comes before the recursion and the string that comes after the recursion. So we see that, in fact, we're now pumping both V and Y as we iterate this recursion. So instead of having 1 pump, we have 2 pumps. A before and an after. So this means that there are 2 very important differences from the regular pumping lemma from this. So first one is the obvious one, we pump 2 parts of the string rather than 1. But the really important difference, and this is what creates most of the headache here, is that the pump can occur anywhere in the string. Before, XY had to occur within the first M characters of the string. No such restriction exists in the context-free pumping lemma. This pump can occur anywhere on the string, but the pump does have a cap to its length, which are based on the number of productions in the grammar, as long as the grammar is in a particular form that restricts the number of terminals that V and Y can pump. And we can create a grammar that only creates a V and a Y of length at most 1 as part of that. So we can place a restriction on the size of that, and that creates a restriction to the length of the window that we look at on the string. It is going to be at most the number of productions in the grammar. So very much like the number of states in the accepting DFA, we're going to have a number of productions in the accepting grammar that becomes a termination point. Yeah.
Could the pumps on either side be different lengths?
Yes, absolutely. Some of them can be 0 or empty, so we can only have a before and not an after, only an after and not a before, or a before and an after that are at different lengths.
But then their lengths are limited to the number of states, so are you then limited to twice the number of states for?
Yeah.
5?
Yeah. Basically, we're going to place restrictions on the grammar and then show that we can create a grammar that's in that form that we can then utilize. Yeah, great question. How are we doing so far? Any questions on this? I think the visualizer will really help to see this. Didn't mean to press that yet. So let's dive into dying. Let's dive into. I'm right here with you. I'm dying too. I have formal definition for it. Let L be an infinite context-free language. There exists a positive integer m that's now going to represent the number of productions in the grammar rather than the number of states in the DFA. This is the number of repetitions of producing something from before and after before we get back to that recursion. The number of productions, that's the maximum size of that recursive procedure. If we have 12 productions, S to A to B, B to C, etc. Once we reach the end, we need some recursion at some point. What creates the longest recursive chain is going back to S. So let L be an infinite context-free language, this integer m, such that any string W, where the length of W is greater than or equal to the number of productions in the grammar, can be decomposed into UVXYZ. Now it's a five-part string instead of a three-part string, such that we know that the length of VXY is less than or equal to m, and we'll talk about why that has to be in a moment. And the length of the recursion, the length of the recursive pump has to be greater than or equal to 1. We have to be able to produce an extra character in order for this recursion to not be a useless production or a useless sequence of productions. If you get from the start of a recursion back to that recursion and haven't added anything to your string, then you can do that an arbitrary number of times and not change the string, which means that it's useless. There's no reason for that recursion in the grammar. So for the recursion to be making an infinite language, we need the length in terms of terminals of that to be greater than or equal to 1. And the way we're going to visualize this is, what are these U, V, X, Y, Z? We talked about V, X, and Y already, but U and Z are kind of like the X from the irregular pumping lemma. This is what's going to get us to the first case of that recursion. Starting with the S, there's no guarantee that that's the start of the recursion. The recursion could be from B to C, to B to C, to B to C, but we have to get to that non-terminal B in order to start that recursion. So the process, the part of the string that comes before that first we get to that recursion, that is U. The end of the string before we get to that recursion is Z. So the part of the string that is created by the time we reach that recursion is the string UZ. We hit the recursion. By the time we get back to that recursion, we've created the string VY, and that is inside of UZ because the recursion was inside of that. Do note that U can be empty, Z can be empty. So there's nothing that says that these characters all have to exist. It's just a substring that may be of length 0. Then we're going to repeat that recursion some number of times, creating some number of V's and Y's, but the portion of the string that goes from the end of that recursion to termination, when we end up with a string, that is the substring X. So I have a good visualizer for this in a moment. So we, instead of having X, Y to the I, Z, we have U, V to the I, X, Y to the I, Z, keeping that I constant for all I, 0, 1, 2, etc. So basically, if a context-free grammar exists for this, and we can break this down into U, V, X, Y, Z for some recursion V, X, Y, I guess for VY, then the string U, V, X, Y, Z has to, for all I, for pumping the V and the Y, also be producible, also be in the language associated with that grammar. So we could prove that a language is not context-free if we could find such an I, such that for any window of length VXY that we pass over it, then doesn't matter, we would end up with something not in the language. So yeah, finite number of productions in the grammar, infinite number of strings in the language. Then there exist derivation trees of arbitrary length in that grammar. Here's the visualizer. We start with our start non-terminal S, and through some number of productions, we reach the beginning of our recursion. As we do this, we've created some terminals on the front and some terminals in the back. by the time we reach this. The terminals in the front are the U, the terminals in the back are the Z. By the time we get to A, via some sequence of productions, we're going to get from the start of the recursion back to the recursion. As we do that, the front characters to that, the front terminals that we produce are going to be V. The rear terminals that we produce are going to be Y. And then going from that to termination is what produces the X in the middle. And so this is how we get kind of in depth first order, U, V, X, Y, Z as the string that is produced as we go through this process. Questions about the visualizer? I'm hoping at this point, at least the intuitive idea of this should click. Ask questions if the intuitive idea here is not clicking. Yeah,
You said earlier that V and Y can be different lengths.
Yeah.
You said on the previous slide that they were both to the same constant.
yeah, so you'd be repeating them. So if there are different lengths, let's say the length of V is 1 and the length of Y is 2, then maybe this is A and this is BB. Then you'd have U, B is replaced with A, X, Y is BB, and then we end up with our Z at the end. I'm capitalizing them here just so like distinguishing between the terminals and what are substrings. They shouldn't really be capitalized, but just to distinguish them. If we pump this once, we would end up with U, A, X, B, 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 Z. So they're a different length, but the I here is 2 regardless. We take the length of this, multiply it by 2 to get the portion of that string that is the B. Take the length of this, multiply it by 2 to get the portion of the string that's a Y. So it looks like, don't pay attention to the area here being the same. This is just via some sequence of productions, we produce some substring B and some substring Y that don't have to be the same number of characters. Great question. Yeah.
So in the UVXYZ decomposition, I don't know exactly what X does.
It's going from the last iteration to termination. So let's give you a basic grammar that we could follow for this. So S arrow, A capital A, B, A arrow. I don't know. B capital A, that's fine. Or A, B, and then we go B arrow, B, B. Why not? I have no idea what this grammar does or if it makes any sense, aside from it needs to be able to terminate. But the whole purpose of this is to be able to break this down into the UVXYZ. So the U is the portion of the string that comes before the recursion starts. So the recursion in this is A to A. So to get to this A to A, you have to produce a portion of the string just to get to that point. So we're going to have an A and a B that we produce before we get to that recursion. So this is our U and this is our Z. It's the portion of the string before and after that gets you to the position of that recursion. So then we're going to do that recursion some number of times. As we do that, we're producing additional characters. That becomes your V and your Y. So maybe we do this just once for the moment. So we see that there's a B and an A, and that creates your B, this is a U, not a V, or B and your Y. We could repeat that an arbitrary number of times. We could do it 0 times. We could do it 1 time. We could do it 2 times. We could do it 3 times. But to get to termination, there's no way to terminate at this point. We have to produce more string in order to be able to have a complete string that is derived from this grammar. So to do that, we have to produce an AA before the capital B and have that become a BB. This is your X, the portion of the string that leads to termination after you're done with the recursion. So just like this string is in the language, we could take out B and Y. We could end up with A, B, B, B. That string is in the language where we have U, X, and Z. We could repeat B and Y. We could have A, B, B, A, B, B, A, B. And we have U, B, B, X, Y, Y, Z. And that string is in the language. We could repeat the B's and the Y's an arbitrary number of times, and it's just representing in this grammar, repeating that recursion some number of times. Yeah.
So then if it was A goes to B little a capital A instead,
A goes to B little a capital A. Yeah.
then would it be that B would be BA and Y would be lambda?
Yeah. In this case, B would be BA and Y would be empty. Absolutely. Yeah. So each one of these is optional. There's no guarantee that each one of these contains or derives at least one terminal's character. A lot of them can be empty, in fact. It just has to adhere to the rules that the recursion produces at least one character at some point. And then the VXY, the length of the recursion plus going to termination, can be at most a number of characters equal to the productions in the grammar. No, you're good.
If you had multiple recursions in one grammar, like multiple elements loop back to each other, would you just
Yeah.
pick the first one that shows
Yeah.
up?
Yeah, the idea is that just like in a DFA with multiple cycles, we're just interested in the first one that occurs after, since in order to have a string that is longer than the number of productions, if there's a cap to the number of terminals that can produce, then we know that strings of a certain length have to have been recursed on at least once. So it's exactly the same idea as the regular, but it's very good to tie it back to that idea. So we'll place restrictions on productions and the number of terminals that they can produce. Then we know that any string of a particular length has to have gone through recursion, which means we can break it down into that UVXYZ. All right, we'll pick this back up tomorrow and hopefully get a good chunk of the way through it. But again, if you understand the regular pumping lemma, it is more complicated. And in fact, the proofs end up being more complicated more frequently, but it's not like learning the regular pumping lemma from scratch, which is a completely new idea. And very hard to learn. So at least office hours starting now. If you want to get started on the homework, get started on the project. Or anything else.